Hi, I'm Bob. Welcome to my solutions to the textbook Econometric Analysis, the 8th edition, by Professor William Greene. I will provide my answers to the exercises and application at the end of each chapter as detailed as possible. I hope they help you better understand what you have learned. I will also post links to some basic econometric concepts and estimation methods that are related to the solutions. We will start with the exercises for Chapter 3 today. It's about the ordinary least squares estimation method. The first question asks us to show the sample sum of residuals E is 0. And the sum of the product of the explanatory variable x and the residual E is also 0. We first write down the population model y equals alpha plus beta times x plus epsilon, where alpha and beta are population parameters, and epsilon is the error term or disturbance. The corresponding OLS estimation model is y equals a plus b times x plus e. The OLS estimators a and b are the estimates for the population parameters alpha and beta. The residual e is the estimate for the disturbance epsilon. Since this is a simple regression model with only one explanatory variable, we can use simple algebra to show the results. The results are the two properties of the residuals after OLS regression. The first one is the sum of the residuals is 0. The second one means the sample covariance between x and e is 0. We can derive them directly from the OLS estimation method. OLS is a method to minimize the sum of squared residuals. The two first-order conditions of the minimization give the two results. The derivative of the sum of squared residuals with respect to a is 0, which leads to the first result. The derivative with respect to b is also 0, which leads to the second result. These two results are also known as the OLS normal equations. This is the case with one explanatory variable. If there's more than one explanatory variable, we can use matrix form to show these two properties of the OLS residuals. This part is not required to answer this question, but it is always better to know more than one way to solve the problem. And it is also because the textbook uses matrices heavily. We can write the population model in matrix form in the general case with k explanatory variables. The explanatory variable matrix X is a n by k plus 1 matrix. The outcome variable Y and the error term epsilon are n by 1 column vectors. The population parameter beta is a k plus 1 by 1 column vector. Please check out more information on the matrix from the link below. The corresponding OLS estimation model is y equals x times beta hat plus epsilon hat, where the beta hat is the OLS estimator and the epsilon hat is the residual. The matrix form of the first-order condition for minimizing the sum of square residuals is as follows. Please find information on the derivation from the link below too. Finally, it leads to the OLS normal equation in matrix form. Then we have x prime multiplied by epsilon hat equals 0. We write the elements of the matrix and the vector out. We find that the sum of residuals is 0, and the sample covariance between the residual and each explanatory variable is also 0. This is the general case with k explanatory variables. Let's solve part B. It is about the solution for the constant term. It comes from the first result in part A. The sum of residuals is 0. Substituting the expression for the residual and using the fact that the sample sum equals n times the sample mean, we can reach the answer. It implies that the OLS fitting line goes through the point of the sample means. Let's find answers to part C. From part B, we have equation 1. From part A, we have the second normal equation 2. Combining these two equations leads to equation 3. Using the fact that sample sum equals sample size n times sample mean, and a constant multiplied by 0 equals 0. And subtracting 0 from both sides of equation 3 gives the OLS estimator B's expression. Let's turn to part D. The second derivative matrix must be positive definite for the solution to minimize the sum of squared residuals. The second derivative matrix equals 2 times x prime times x. For a simple regression model with one explanatory variable, we can write out the elements of the explanatory variable matrix X. And find that the two diagonal elements of the matrix are both positive. We then calculate the determinant. Using algebra, we obtain the answer. Let's solve exercise 2. It is about the sum of squared residuals. Suppose B is the least squares coefficient vector in the regression of y on x. We know that the OLS estimator B minimizes the sum of squared residuals. In other words, the sum of squared residuals from an OLS regression is smaller than any other sum of squared residuals from the estimation that is not OLS. So the difference in the two sums of squared residuals in this exercise should be positive. This is the logical reasoning. We can also show it using algebra. If we have another vector c, we can write the vector c equals the vector b plus a vector psi. Replacing c with b plus psi, we can write the first sum of squared residuals into 4 terms. Note that the middle 2 terms are the same because they are scalars, or numbers, and the transpose of a scalar is itself. And they are both 0 by the OLS normal equation. So the difference in the two sums of squared residuals equals the product of the transpose of a column vector and the column vector itself, or equivalently, the product of a row vector and its transpose. We know that the product of a non-zero row vector and its transpose is always a positive scalar because it is the sum of squared components. Thus, after we replace psi with c minus b, we reach the answer. Let's do exercise 3. It's about the partial effect or the parceling out interpretation of the OLS coefficient in multiple regression. According to the Frijns-Level theorem, in the least squares regression of y on a constant and x, to compute the regression coefficients on x, we can first transform y to deviations from the sample mean of y, and likewise transform each column of x to deviations from the respective column mean. Second, regress the transformed y on the transformed x without a constant. We write the population model as follows. We divide the explanatory variable into a column vector of 1s and the other explanatory variables matrix x2. Define the residual maker matrix M0, where the uppercase I is the identity matrix with 1s on the diagonal, and the lowercase I is the column vector with 1s. Then, the population model is pre-multiplied by M0 on both sides. We can show that the first term is 0. We have equation 1. Applying the OLS method to equation 1 gives the estimator beta 2 hat, which is from the regression of M0y on M0x2. M0y is a vector of the deviations of y from its sample mean. And M0x2 is a matrix with k columns of deviations of x from their sample means. Therefore, beta 2 hat is the OLS estimator from the regression of transformed y on the transformed x. Next, we show the second version of the Frisch-Wahl-Lowell theorem. That is, we can get the same result if we only transform x. We write the expression of beta 2 hat with the transformed y and transformed x. Using the fact that the residual maker M0 is symmetric and idempotent, we can show that beta 2 hat is also the OLS estimator from the regression of y on the transformed x. But we cannot get the same result if we only transform y. We can verify the Frisch-Wahl-Lowell theorem in Stata. Please download the dataset bobg1.dta for this exercise. The data come from the Panel Study of Income Dynamics PSID survey. We have collected data on the US workers' wages, gender, education, and other information. Let's regress log wage on schooling. The estimate of the return to education is 0.131. This is an OLS regression with a constant term. Then we generate a constant vector of ones and regress log wage only on the constant. We store the residuals, which is the transformed y. Similarly, we obtain the transformed x. If we regress the transformed y on the transformed x, we obtain the same estimate for the return to education as in the original regression model, 0.131. We can also verify that using only the transformed x gives the same result, but using only the transformed y does not. Let's solve exercise 4. For the population model, y equals x times beta plus epsilon. We define the residual maker matrix M. Then we divide x into two sets, x1 and x2. The population model can be written as follows. x1 is an n by k1 matrix that contains k1 explanatory variables. x2 contains the other k minus k1 explanatory variables. We define the residual maker matrix M1. Then we can write M1 multiplied by M into two terms. The first term is M. The second term is an n by n matrix. We consider the transpose of the last part, M multiplied by x1. According to the residual maker, M multiplied by x1 results in an n by k1 matrix. Each column of it is the vector of residuals in the regression of each column of x1 on all columns of x. The residuals will be 0 because the explanatory variable x contains the outcome variable x1. In other words, M times x1 is an n by k1 matrix of zeros. Therefore, its transpose is a k1 by n matrix of zeros. Return to m1 multiplied by m, it equals m. Thank you so much for watching this video and doing the exercises with me. I hope they are helpful to you. See you soon in the following exercises. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.